Yeah, I think now you're appearing in YouTube. For the Q&A, the questions will be posted in the YouTube chat window, and then I can ask the questions at the end of the talk.
Yeah, that will be better, because I won't be able to, it will be difficult for me to check and everything. So
okay, I'll take care of it.
Sure, that would be nice. So initially, do you want me to, share the screen, or just do you have the video, or?
You can share your screen. I think
right now the way it is right now. Okay.
Yeah, that should be fine.
All right.
So another 2-3 minutes is there?
Sure, no issues.
Okay, thank you. So can we get started? You're okay?
Yeah, sure.
Okay. Okay. You're.
Because my network is showing some problem, but you can see everything correctly, right?
1 second. Now it's good.
Okay.
Okay. Good evening. My name is Varun Raghunathan. I'm an assistant professor in the ECE department at the Indian Institute of Science, and I would like to welcome you all to this second ECE webinar. This is the second in the series of webinars we have planned across the academic year. And this talk will be given by Dr. Goutam Chattopadhyay, and he is a senior research scientist at the NASA Jet Propulsion Laboratories in Pasadena, California. And he's an expert in millimeter wave technology. And he is also an affiliated faculty with the California Institute of Technology Division of Physics, Mathematics and Astronomy, and he is also a BEL Distinguished Chair Professor at the Indian Institute of Science in Bangalore, and also an Adjunct Professor at the Indian Institute of Technology in Kharagpur. And his research interests are mainly in microwaves, millimeter wave, terahertz receivers and radars, and also the development of space instruments for the search for life beyond Earth. And he has many awards to his credit. He is a fellow of IEEE, IETE. He has also been an IEEE Distinguished Lecturer as well. Right. And with that introduction, I would like to welcome Dr. Goutam Chattopadhyay to give this webinar. And just a quick house rule, like if you have any questions, I would like to request you to post it in the YouTube chat box, and then we'll be taking up the questions at the end of the talk. Right. Okay, so Professor Dr. Chattopadhyay, it's all yours.
Thank you, Varun, for the introduction, and thank you everyone for joining in. I thought that what we'll do is I'll give you a kind of overview of what we are doing and how the design and innovation plays a role in development of space instruments. That's why the title of my talk is Design and Innovation, Sensors, Antennas and Systems. So let's get going. So I want to acknowledge my group members. We have a group of about 24 people. The name of the group is Submillimeter Wave Advanced Technology SWAT. This is not the kind of SWAT that you see on TV. This is a different kind. So you can, if you look at the faces of the people on this chart, you will realize that they are from all over the world. So I always tell people that one of the reasons for the success of NASA is its diversity in workforce, diversity of ideas, and that's what makes us, because we get people from, experts from all over the world. They're the best and the brightest, and we are really lucky to have, my colleagues who are working with me. This is amazing. So before I start talking about it, I want to show two new things that has been happening over the last, a month or so. If you have been following the news articles, last month there was a paper in Nature Astronomy on the detection of phosphine in Venus. So they believe that the question came up that is there life on Venus? So I'll spend a little bit of time, discussing why this is important and what kind of instrumentation that go behind this kind of measurements. So why phosphine detection is so important in Venus? What does it mean? What it means is that Venus is a very hostile environment because the temperature of the surface of Venus is about 700 degrees centigrade, extremely hot. Then how life can survive? But what they are claiming is that not on the surface, but in the atmosphere of Venus, that is about 60 kilometers. If you look at 60 kilometer altitude, the temperature on Venus is about very nice, about 20 degrees centigrade or so. And they've detected phosphine in the order of about 10 parts per billion. So if you look at Venus atmosphere, so from where the phosphine is going to come, phosphine is actually one of the components of that for life, the kind of life that we know, carbon-based life. We need few elements for carbon-based life, and we call it CHONOPS, C, H, N, O, P, and S. That is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the building blocks of life that we know. And then the 10 parts per billion on Venus is actually high. The reason is Venus doesn't have, if they're abiotic, the non-biotic source, then we should not get 10 parts per billion. We see phosphine in other planetary bodies like Jupiter and Saturn and other places, and the source of them, basically they are from volcanic activities or from solar winds, and as well as for lightning. But Venus is not enriched in hydrogen. Then how this phosphine of 10 parts per billion is coming from? So that they are thinking that it could be because of a biotic source, because otherwise the chemistry that we know it cannot explain. This detection was done from Earth-based antennas. They were done at 267 gigahertz. That is our line of work. And there is another line, actually much stronger line of Venus at 533 gigahertz. So, however, when this paper came out, it created a lot of buzz, but immediately people started looking at more closely and then said that, okay, reanalysis of if you see the articles in Astronomy and Astrophysics, they are saying that is not possible. And then the next paper just coming out, actually day before yesterday, they're saying no phosphine in the atmosphere of Venus. So, and I show one Bengali article on the right top corner that is I wrote. It is in a newspaper article. So why I'm showing a newspaper article for in a scientific discussion? The reason is this, that as a scientist, sometimes we'll have to take up on us to educate people, to let people know science in layman's term. That's very important, and because sometimes you will see in press and other places, they say things, they claim things which are not really true, because I've seen other places people are saying, oh, we have already detected life. So we have not detected life. We have just, they're claiming we have detected phosphine. That there's no claim that life has been detected. So I wrote something about that. So this is very interesting. And why I'm saying this, because this discovery was done. Whether it's true or not, we'll have to actually go to Venus again and do some measurements from a space-based mission, because we cannot really do a lot of things sitting in here. And so it is very, very important. And these are frequencies of submillimeter waves. So in the goes from about 200 gigahertz to 600 gigahertz range, we can do these kind of detections, and we have the capability. We are building instruments. We have actually proposed before to do exactly the same kind of measurements, but unfortunately, because of a lot of constraints, funding constraints, it was not selected. So now it is much more important that we actually have a Venus mission. India has been thinking about a Shukrayan mission. It was 2 years ago. There was a lot of push for that, and now it was in the back burner. I think now it is very important if ISRO plans a mission to Venus. So that's the reason I thought that I should mention that. The next thing I want to show is about this happened earlier this week, or I think last week, that molecular water detected on the sunlit moon, sunlit side of moon by SOFIA instrument. So that is very, again, what does it mean? It means that, if you go to moon, we knew that there is water in moon, but mostly that is in a very cold and shadow area of moon. So we have not really had detected a moon on the sunlit side on the surface before. But this Nature Astronomy paper, again, it came out, they detected for the first time. SOFIA is an airborne instrument. So on a 747 airplane, they have a big antenna, and so this is for astrophysics mostly, but for the first time they looked at moon and then they detected at 6 micron. This is a high resolution spectrometer at 6 micron, because they used to do measurement at 3 micron, but there it was not possible really to say whether they are detecting really water, H2O, or the hydroxyls. So it is. However, we know that water, the strongest line of water is actually 557 gigahertz. So we have been, again, we have been building instrument to go to moon and detect water on moon. You'll say, what is the big deal about having water in moon? Okay, you know that NASA has this Artemis project that is coming up 2024. We are having a gateway to moon. It is like our space station that we have, similar to a space station on moon, so that astronauts could go to the Artemis and then land there. And if water is available on moon's surface, that makes life much easier. However, the amount of water that was detected by this measurement is not that much. If you think about it, it's about 350 milliliter of water in 1 cubic meter of of surface material. If you compare it, this is 100 times less than the 1 cubic meter of sand in Sahara Desert, which means it's drier than Sahara Desert. So it's kind of not much at all, but still is important. And it's not for the drinking water for the astronauts. It's much more than, that for fuel, for rocket fuel, we use oxygen and hydrogen. So idea is that if the water really exists, you can go there and you can actually separate from water, oxygen and hydrogen, and that you can use as fuel for future. So that's why these two are very important. And again, these are all, we can build instruments at terahertz frequencies, 557 gigahertz, and actually go and map it out to go to moon, map it out how the water is distributed on moon surface on the sunlit side. That is very exciting. So this actually leads very well to what I wanted to talk to you all about. So what I thought that I'll give you one example of the instrument that we build and the innovation that goes behind it, and to answer a big science question. So we are building an instrument, it's called WhatsUp, Water Hunting Advanced Terahertz Spectrometer on Ultra Small Platform. I came up with this acronym. So because we wanted to find out what's up with water. So what do I mean? I mean is that actually when our Earth was created, there was no water. Scientists believe that comets brought water to Earth. So how do you prove that? If someone tells you that, okay, we believe that comets brought water to Earth, you will tell that I don't believe you. Prove it. How do you go about proving that kind of hypothesis? One of the things that we can do, that water has different colors. That that water that we drink every day, H216O, which was detected on moon, on the moonlit surface, sunlit surface of moon, it's H216O. That is a spectroscopic signature at 557 gigahertz. However, there are other kinds of water. H217O, that is 17th oxygen isotope, that also forms water, 18O, and HDO, hydrogen, deuterium, and oxygen also forms water, that is at 509 gigahertz. So if you can see that 509 gigahertz is HDO, 557 is 16O, then 552 is 17O, and 547 is 18O. So all these different lines, if we do high resolution spectroscopy and take the ratio of the abundances of different kinds of water, of course, most abundant is H216O that we drink every day. If you take the ratio of these abundances and do a D over H ratio, how much of deuterium or hydrogen is available in this water, that gives us a clue that what is the source. Because if those ratios are similar to some of these comets that you are seeing, then the sources has to be the same. So far we made only about a dozen of such measurements. So it is not statistically high enough. So we have to this question is still out there. What's up with water? And that's why we are building an instrument to in a CubeSat. CubeSats are shoebox-sized satellites. I'll talk more about it. And we are building an instrument that is, very low power and low mass, because whenever you are building an instrument for space, the main driver is power and mass, because every kilogram of mass that we launch is cost huge amount of money, the new technologies, and available powers for these are very, very low. So this has to be, you have to build an entire instrument which should draw hardly any power. How much power I'm talking about? 10 watts. 10 watts is not, less than a light bulb. So, but your entire instrument needs to work on that kind of power. So that's what I'll talk about, what kind of innovations that we need to do to come up with this kind of instrument. So we are building, as I said, we are doing a CubeSats and small sats. CubeSats are shoebox sized satellites. So they are, they go by the size of one. U stands for cube of 10 centimeter by 10 centimeter by 10 centimeter. But if you are trying to build a science instrument in a CubeSat, then we kind of think that you need at least about 6 U of size, because you need 1 U for spacecraft housekeeping. You need some solar panels, and you need some telecommunication star tracker so that we know where we are, and then the scientific payload. So that we need some space. But again, it is 6U is 30 centimeter by 20 centimeter by 10 centimeter, just like a shoebox. So it's not big at all. So you have to build entire instrument in that kind of space. That is very, very challenging. So we have launched a lot of CubeSats and small sats, and many of them are in the planning all over the globe. All the space agencies are doing one of the important thing, because I'm talking to at students at IISc and faculties at IISc. In the US, lot of CubeSat work is done at the undergraduate level at the universities, because students can actually get together. They can put together some instruments. Of course, they might not be space qualified scientific payload. However, they can do a lot of stuff. They can do a hands-on experiment with CubeSat and then approach these space agencies or private companies with their main mission. They can always launch the small CubeSats and they can get some data. So this is very, very exciting in that way as well. So one of the key to do, this, you have to build an instrument in a CubeSat, it's miniaturization and integration. If you look at what I'm showing here, this is a iPhone 5S circuit. So if you have not opened your smartphone ever, you should go ahead and do it, because what you will see is what it means to integrate something. You can actually design some stuff. You can design a chip, you can design some kind of components, but how everything comes together is very, very important. And this is, smartphones nowadays, this is a piece of art. If you open it, you'll see the connector that they use, what level of integration, what level of thermal management, because there are so many antennas, they have a power amplifiers. How do you manage the thermal part of it? So each smartphone has so many antennas, 5 to 6 antennas, all these different, 2G, 3G, 5G, Wi-Fi, different kinds of Wi-Fi. So you'll have Bluetooth. So you'll have to see that all this thing has to come together. And for space, we are actually taking advantage of all this development that has happened in the cell phone industry, and we are trying to leverage that for us. So we are. I'll show you that in CMOS, 65 nanometer CMOS, we built W-band 90 gigahertz synthesizer that hardly draws any power or anything. So we are actually taking the advantage of what has happened in the other industries for application in space. And so we need low power and low mass instrument. We need to have very high level of integration. As I was saying, that we are taking advantage of the CMOS industry, and we need to come up with innovative calibration, because you have to calibrate your instrument. This one, I'm giving a specific example that we are trying to measure very precisely the abundance of H216O, HDO, and take the ratios of these. Then if you do not have a calibrated system, how do you know what you are measuring? So how do you calibrate this kind of system? One of the way we do is it's a radiometer and spectrometer, is that there's two temperatures, very well-known temperature. If you look at two temperatures and basically two levels of signal, and then we can actually compare and say, okay, this is the gain of my system, and this is what the detection level that we are going to get. Because as I said, for the phosphine case, it was 10 parts per billion, and sometimes we measure parts per trillion as well with this kind of sensitive receivers. So we need a calibration system, and the most common calibration systems can be Dickey switch, Unfortunately, when we are building an instrument at very high frequencies, terahertz frequencies, we don't have a switch available. So we developed a MEMS-based switch. We need to develop also a load, very well calibrated load. And then one of the big elephant in the room is an antenna. So I'll talk about that as well. So these are the things I'll focus on and talk about. This is the sub-millimeter wave heterodyne spectrometer at room temperature, that WhatsApp instrument. So if you look at this, we have a low profile antenna, and as I was mentioning, the frequencies that we are targeting is the HDO at 509 gigahertz, 547 H to 18O, 552, 17O, and 557. This is 16O. We have to have a low profile antenna. We are going for 18 centimeter aperture. Why? Because the available, if I mentioned, this is a 6U CubeSat that is 20 centimeter, 20 centimeter, 20 centimeter by 10 centimeter by 30 centimeter, right? So we cannot have a larger antenna because folding and deployed antennas are not possible at this frequency, at least now. So we'll have to have and again the antennas will be low profile because we cannot have a small shoebox size satellite, something sticking out big. And then we'll have to develop a switch, calibration switch, and we are going to use subharmonic mixer, gallium arsenide Schottky diode based mixer, and we have to generate the local oscillator, and we have developed a synthesizer, CMOS 65 nanometer synthesizer working at W band and giving low phase noise and frequency multipliers. And then we go through the amplification, and then at the back end we also developed a spectrometer. Again, this is a SoC system on a chip based 3 gigahertz bandwidth, 4096 channel spectrometer, which means that we have this is like your spectrum analyzer on a chip, and that has every the resolution bandwidth of your then spectrum analyzer is about 750 kilohertz. So that is the kind of instrument that we are developing. So we also developed a switch part is a MEMS based calibration switch. I'll talk about it, and then all these different components that we have to develop. So in terms of antennas for CubeSat, so we have been developing antennas for CubeSat for some time now, but they were at low frequencies. As the first CubeSat, interplanetary CubeSat that we developed is called Mars CubeSat 1. So what the reason we developed this was that whenever we go to Mars, that right now Perseverance rover is on its way to Mars. So whenever we go to Mars, when the spacecraft enters in the Mars atmosphere, like inside spacecraft that is going in, there is no direct communication to Earth, which means for about 7 minutes of its journey, we do not know what is the health status of our spacecraft. And did it really land safely? It takes about 7 minutes because there is no direct communication. What we have is a satellite called MRO, Mars Reconnaissance Orbiter, that is going around Mars, and it communicates with MRO, and the MRO sends the signal back. On top of that, it takes about 7 minutes for light to reach from Mars to Earth. So we have this. So to avoid that, so what we thought that with the main mission, can we launch 2 CubeSat, shoebox size satellites, which will have 2 communication links. One is a UHF transmission link that will communicate with the spacecraft that is going down, and we'll have a K band. We need high gain antenna. Sorry, not K band. This is the X band that we showed. X band transmission that will have a DTA, direct to Earth communication. So this will get data from the health data from the spacecraft, and then it will transmit to Earth, so that we'll have real-time information about what is going on with that, how it is going down. So for that, we needed to develop X-band antennas, the foldable antennas. We developed these are reflect arrays. My colleague Nasir Chahat and others, we were involved in developing this, and then we have the feed that actually sticks out. This is not really very low profile, though this is a flat antenna, because you'll have to have a feed that is sticking out. So we developed, and it actually worked very well. So it gave data when inside spacecraft was going down to Mars. So it was that gave us confidence that we can actually use these kinds of systems. Another thing that we developed is called RainCube. This is a radar on a CubeSat, and there, if you see it here, this is of course an animation that's showing that we needed a 50 centimeter antenna at Ka band for this radar. So what we did, you can see here, this is a 20 centimeter by 10 centimeter by 30 centimeter, again 6U CubeSat, but the antenna that needed to be there is 50 centimeter. How? And we are given only 10 centimeter by volume to store this antenna. So how do you make a Ka band antenna that is 33 gigahertz? How do you make that an antenna and store in such a small volume? So that was the challenge that we had, and we came up with this mesh foldable antenna. I call it umbrella antenna. I will see why I call it. Of course, my colleagues, Nasser and all, they get upset with me when I say umbrella antenna. You can see it here. This is fully deployed. So there is a feed horn here. This is a Ka band this is flare angle horn, and then there is a sub reflector that needs to be again launched. I'll show you in a video, and then this is the mesh antenna that is foldable. It actually worked. Let's see if the video works. So in the lab, you can see this spring loaded. You just release it. I hope the video is playing well. Sometimes because networks, you can see it is getting deployed. That's how it gets deployed, and then the sub-reflector has to deploy again. So that's how it actually deploys, and it is actually doing measurements right now, and it's doing really well. So this worked. It was very challenging because we are talking about Ka band, but how do you go from Ka band to higher frequencies? We are talking about here 550 gigahertz. So we cannot really use that kind of technology that we developed for RainCube. So we'll have to come up with new ideas, and we were scratching our heads, and then we came up with three different antenna technologies. Let me tell you that. That's what I was talking in the title. I have the innovation part is there. So we came up with meta surface antennas, and what you see here, this is a all metal meta surface antenna. I call it fakir bed antenna. Why I say that? You all know that fakir, the term fakir means saint, in Sanskrit. So what they used to sleep on bed of nails, and if you look carefully, these are all metal nails that is sticking out. So how does it work? This is a meta surface antenna, all metal structure. This is, in space, all metal has a lot of advantages because dielectrics can actually charge up. So if you can avoid dielectrics in space, it is there's advantages. So we thought about all metal structure. This is a 300 gigahertz fakir bed meta surface antenna. How it works is that you can see at the center there is a circular waveguide, but for circular waveguide, the most dominant mode, is T11, but to have a surface, we need to generate a surface wave. So, and as the surface wave propagates on this structure, if we can modulate the surface wave, then it radiates in the broadside direction. So we had to actually change, we have to generate a TM01 mode from T11 dominant mode that becomes a surface wave, and then we need to modulate that surface wave. What we did is we actually developed these pins of different height pins. You can see here. So at 300 gigahertz, the height of these pins are the longest one is about 120 micron. Thickness of our hair is about 50 micron to 150 micron. So we are talking about this, the thickness of this antenna is one thick hair. So as a result, it is very, very low profile. This is all metal. You can just put this antenna on the side wall of the CubeSat itself, and it's so low profile. As you can see, as I said, the thickness of this, entire antenna structure thickness will be less than a millimeter. And then just a circular hole, and you can put your instrument behind it, then it becomes the sidewall itself becomes your antenna. We fabricated it using for 300 gigahertz. We did silicon micro machining, and then we we plated it with gold. You can see it here, and it worked very well. So that gives us the confidence that we will be able to use these low profile antennas for future. And another one that we want, one of the problem, not problem really, one of the challenge that we have to overcome, the efficiency of these antennas are not very high yet, and also the bandwidth is somewhat limited. So we are trying to overcome those. Now we have improved quite a lot. We can get now about maybe 70% antenna efficiency. And also we are trying to improve the bandwidth, but that is a bigger challenge. People who work on metasurfaces, So we also looked at other kinds of antennas. So can we go ahead and develop some other kind? Still, they have to be low profile. So we came up with a lens antenna, silicon lens antenna with a leaky wave feed that is also low profile, very different than other kind of antenna. So if you have a leaky wave feed, and then of course you need to do some matching. You can see on the right side. So you have an input waveguide, and then you generate the leaky wave. That means there is a gap here, and then you'll have to have some kind of matching layer, and because silicon is very high dielectric constant, and then you put a very thin lens on top, then it becomes a good antenna. So we went ahead and fabricated one. This is eventually we need to make 18 centimeter, but the one that we fabricated is at 8 centimeter, just to see if it works or not. You can see here, this is the fabricated antenna, very thin layer of silicon lens on top with anti-reflection coating, and total thickness of this is about 7 centimeter. So that is pretty low profile. If you want to use a standard reflector antenna, that will be much larger in terms of the thickness and the volume. So it works really well. You can see the far field radiation pattern. So this, we thought, okay, this is what we are going to use. But we also thought that, okay, as a backup, because in the space, if it sticks out in space, we'll have to go through all these vibrations and all. It's not that it's a big problem because they're small, we can do that. But I wanted to have a backup, plan B. And so we developed a low profile reflector antenna as well. So you can see here, this is a reflector antenna. This is the actual, the fabricated antenna at 550 gigahertz. So it works from 500 gigahertz to 600 gigahertz. And this is a small sub reflector here, and we wanted to reduce the blockage, so that we came up with new mechanical structure design in a way, and the feed comes behind. This is the feed, this is the backside through the hole that you see, but this is a very low profile antenna. It is not a standard reflector antenna, and we found that this is working really well. So this can go, I'll show you some pictures that how we are integrating that entire structure. So these are the three antenna options we have. To show, we wanted to show we do a demo on a balloon instrument. The idea was to do that this summer, but again due to COVID, we got delayed. So we are planning to do that, next spring. So on a balloon before we actually go on a CubeSat. What are the other things that I said? We need a SoC based synthesizer. Synthesizer, why it was needed? If you think about it, since if you buy a standard synthesizer from off the shelf, they draw a lot of power. They draw about 6 watts of power. But if our overall budget of the power budget is less than 10 watts, we cannot spend 6 watts on a synthesizer. So we developed a SoC based synthesizer using 65 nanometer node, and this was Adrian Tang. He is my colleague. He actually is an expert on developing this kind of chips. So he did that. This is a 90 gigahertz, a W band 90 gigahertz synthesizer on a. This is the board, but the synthesizer, the chip goes there, and it is working really well. If you see this, the performance of the phase noise performance is 90 dBc per hertz at 1 megahertz offset. So that is good enough for us, and it's drawing only 200 milliwatt of power. So you can think about it, if from 6 watts, we brought it down to 200 milliwatt. This is a huge kind of game changer in this area. And then we also needed a back-end spectrometer, as I mentioned, a spectrum analyzer, because we are actually analyzing the spectrum at 509 gigahertz, 547 gigahertz, 552, 557. So if you FPGA based, or if you buy a standard back-end spectrum analyzer that goes on an instrument, it costs a lot of mass and power. The power is about 8 watts. If you actually 3 gigahertz bandwidth spectrum analyzer is not easy to get, because you'll have to do your ADC needs to be at 6 giga samples per second. So that is not easy at all, you all know. And then you'll have to have this is everything, FFT analyzer and everything on the chip. So Adrian Tang, again with his colleagues at UCLA, Professor Fang Chang and others, we went ahead and developed this SOC backend spectrometer. This is 3 gigahertz bandwidth and 4096 channels that I said, and it draws only 1.6 watts. So from 8 watts, we brought it down to 1.6 watt. That is again huge improvement. Without these two developments, we could not have done put together this instrument. So it was very much needed. Then the next thing is, as I was talking to you, is we need a calibration system. So if you look at this was actually previous generation of WhatsApp instrument, where the entire instrument on the left side of the screen here you can see, but on the right side, what you see here, this is our calibration system. So we had a flip mirror, so we need a motor. There is a mirror, the signal comes in from the sky, from this side, from the antenna, and goes to our receiver through this horn antenna. However, if the mirror can actually direct the beam either to the sky or to a known load, you can see here, this is a calibration load, but this is the motor, so it needs power and it needs a lot of volume. So we thought, can we come up with a low loss switch that can be used for calibration? So we developed a MEMS based calibration switch. What you can see here, how this works is very interesting, that we know that waveguide, these are all waveguide based system. So waveguide essentially is a high pass filter. So if you change the A dimension of the waveguide, you can change the cutoff frequency of the waveguide, right? So if you take a septum, metal septum that you insert in waveguide, and if you put it in and take it out, then you can actually make that waveguide under cutoff or trying transmission. So using that technique, we actually came up, you can see here that the input signal comes in and there are two waveguides going in and two arms which has a septum that can go in and out of that waveguide to make one waveguide under cutoff, other one open, so that you can either see the sky or there will be an integrated load that you will see. And this is in a waveguide, very small, low volume. So we developed that. You can see this is the actual picture. So here what you see on the right side where my cursor is, these are the two waveguides, the black structure, the rectangular, and then these are the arm, the septum, that is metal septum that connected to this MEMS motor. They move in and out of this simultaneously. I have a video to show, but before that I wanted to show how that works. It's a very small structure you can see here. So hopefully the video will work. You can keep an eye in the orange two blocks. That's where you can see that the septums are going in and out of the waveguide, and it's making a switch, and it's a very low loss switch at less than 1 dB of loss at 550 gigahertz. So this is the MEMS structure. We apply about 40 volts it doesn't draw much current, but we need 40 to 50 volts for actuation of the MEMS, and that's how it works. This is a very highly integrated, low mass and low power switch that replaces our these kind of motor flip meter and everything. So that's what we are developing. Sometimes my network doesn't gives trouble, so if you cannot hear me, please let me know. Okay, so then next, the load, calibration load. I told you that for the switch we need to have a calibration load. So what we did, we developed a thermally controlled calibration load in a waveguide where you can heat it up, and you have a lot of sensors. You have a PID controller so that you can maintain the temperature. So we need a linearly changeable temperature load, and that is very highly matched so that this waveguide can connect to the load. We have developed that as well. So this is a programmable calibration load, thermal load. So that now we have all the components that we need to make the instrument work, so that we can put it together in a small CubeSat, small volume of CubeSat, and then we can you can build multiple of them so that we can go to multiple comets. And so there is a mission to Mars on its way. It can throw us out because they're small CubeSat, and we have our own propulsion to go to a comet, and then we do this kind of measurement. So that is the idea of this. So this is the instrument that we put together with the that lens-based antenna that we are talking about. So this is the total mass of this instrument. This is the entire instrument that this is the synthesizer, this aluminum block that you see here, box, and this is the back-end spectrometer that you see, and we have all these terahertz hardware. That is the feed, and there is a MEMS switch, frequency multipliers, and amplifiers, then IF system. Everything is already integrated here. It weighs less than 2 kilograms and draws less than 5 watts. So 1 watt is your actually night lamp that we use. This is 5 watts. So this is hardly any power. So that is a big impact it is going to have on the instrument that we develop for future space missions. And so last year we wanted to, this is in a balloon instrument, we wanted to demonstrate this. This was the last year we showed a precursor to this instrument. We actually flown on a balloon. This is the gondola. And so this year what we thought that we will make our instrument in the CubeSat frame, and then put this entire instrument, this CubeSat instrument, in a balloon gondola and fly. So we have changed, as I said, that we are using now this low profile reflector antenna. So this is what in the lab right now. We know that we are working from home, since March. So we have been it's been really slow, but still we made a lot of progress recently. Few people can go at a time to our lab, so we were able to putting it together. So this is where this low profile antenna is. This just last week we are able to started putting it together. These hardwares came in, So this is this low profile antenna. You can see the feed. We'll have to connect still all other hardware. This is the synthesizer, double band synthesizer, and behind what you see is a CND. This is the control and data handling. So this is the first generation. We are also developing high voltage CMOS. We did. I think there was some. Can you see my screen again? I thought there was some problem.
Yes, now I'm able to see.
Okay, yeah. So there was, network. Sometimes, nowadays everyone is using Zoom and WebEx and, Microsoft Meet, so the bandwidth goes down. I'm sorry. So here we the CNDH board that we made the first generation with discrete component. We have some chips, but discrete. That's why it is kind of large. The next generation we are now that it works, we are going to make an SoC and some other circuits will be there. So it will be cut by half this size of this board. So this is the entire instrument that will be there. We are planning to fly it sometime April next year, but everything. Varun, can
Yes.
you hear me?
Yeah, there was a little bit of some glitch, but now it's.
Yeah, so it's happening more and more, so I don't know. So again, I have put it back. Just hopefully,
Yeah,
I have only two more. I have two more slides. Hopefully, we'll be able to get it done. So this is the plan that is almost there. So next year, sometime April, we'll be flying on a balloon, and then eventually we'll be flying on a CubeSat. So I want to end with something else completely altogether. So this is a Mars helicopter. Many of you know that with the Mars, the Perseverance rover that we are sending an Ingenuity helicopter as well. So what is the big deal about helicopter on Mars? That's because, how the rover works on Mars, that if the rover goes there and this is our rover is the most expensive autonomous car in that way, because it actually drives on its own on Mars. But we pre-program it where it should go, what kind of experiments it's going to do, and so it has a limited capability of where it can go. So we thought that if we put on a small helicopter on top of our rover, then the helicopter will have some sensors. It can take off, go around and do some reconnaissance and send the data back to the rover, and then based on the information it gets, the rover can decide to go where it wants to go. So it sounds very nice. However, sending a helicopter, flying a helicopter on Mars is much different than flying a helicopter on planet Earth. When you fly something on a helicopter on Earth, the blade, the rotor blade that goes around, the RPM is about 400 to 600 RPM, so revolution per minute. But Mars has much lighter atmosphere. So to have the lift that we need, the blade speed has to be about 2600 RPM, and also these people, they came up with multiple blade structure, so that is lightweight and has the required lift. Entire instrument helicopter weighs 1.4 kilograms. It needs about 202 watts of power. So it has some solar cells, and also it has a battery that it charges from the rover. But again, you cannot slap a huge battery because then the weight will go up. And we actually tested everything we have in our lab, a Mars kind of environment, all this light atmosphere and everything. And there we flew this and it works well. So it is a tech demo. So it is going to on rover. We want to see whether it works or not. So I'll end with this picture. This is the Ingenuity helicopter already just before it was actually mounted on our Perseverance rover. It will land there in February 2021, keeping our finger crossed. Let's see how it goes, how it works. With that, I will end. Thank you very much.
Okay. Thank you very much, Professor Goutam Chattopadhyay. And there are a few questions which are posted, and to the audience, I would also like to request that if you have any questions you would like to ask Dr. Goutam, please post it in the chat window in YouTube, and we'll be taking it one by one. So the first question is from Devdeep Sarkar. What were the challenges in the simulation and analysis of electrically large metasurface antennas at 300 gigahertz? Could you please comment on the computational tools and platform?
Yes. Hi, Devdeep. Good question. We had to develop, some kind of analytical, tools first, because as you said, it's really difficult to do with available, softwares to, simulate these kind of structures. So what, I had a Marie Curie fellow from Europe. He came, his name is David Gonzalez. He came, he was also worked with Stefano Macci in Italy. These are all experts in metasurface designs. So we all worked together, and David actually developed some semi-analytical tools to actually much simplify the entire design, and then we simulated with his software tools, and then to verify it, eventually we did use some other available commercial software, but it takes huge amount of memory and a lot of time to you cannot really optimize and design with the commercially available software tools. So you'll have to develop your own tools to do the design part, but available memory and computational resources that we have, with that maybe you can verify, maybe not the entire structure, but some part of it. So that's how we went about doing it. But yes, it is not easy. So you'll have to do this metasurface structures. You'll have to come up with your. We actually wrote some papers on that. Is available. If you do a Google search, or if you want, I can send it to you to show that what exactly we did. How we developed the impedance model. And then we went about solving this problem.
Okay. Next question is from Anik Biswas. At that high frequency, like greater than 100 gigahertz or terahertz, what type of materials are used to make antennas?
So these are all metal structures, that as you can see that normal metals, we use gold coating. It works well, but again, they become lossy. So another thing that we use that I showed you the silicon lens structure, that one of the reason you go for lens quasi-optical designs to avoid the losses. If you take high resistivity silicon, resistivity has to be high, not your normal silicon. If the resistivity is 10 kilo ohm per square, that kind of resistivity if you use, then they are transparent at terahertz frequencies. So they're very, very low loss. High resistivity silicons are very low loss. So when you are using a quasi-optical lens, again, I thought there was a blip in network.
Yes. Yeah.
So if you are using metal structure, you'll have to use gold coating. Again, gold normal at low frequencies, gold conductivity is 4E7, 4 times 10 to the power 7 Siemens per meter. But as you are going in higher frequencies, that conductivity starts going down and down. Maybe at 1 terahertz, we can get 1 E7, so a factor of 4 less conductive gold at terahertz than at 100 gigahertz. However, also the losses depend at metal losses also depend on your surface roughness. So you'll have to pay a lot of attention that how smooth you can do, because when the current is flowing on the side walls of your waveguide, then if your surface RMS is not good, then what is happening is the current has to go much longer path, and that's why we get more loss. So we'll have to pay attention to all those details, but in terms of materials, we mostly use metal or some lens based in the silicon, high resistivity silicon lenses.
Okay. Deepanjan Gop has a comment and a couple of questions. Thank you so much, Professor Goutam. Enjoyed very much. You must have faced so many system level hardware challenges, example, thermal, mechanical, electromagnetic, etc. How did you go about doing the system integration?
Yes, hi Deepanjan, very good question. So yes, so one of the challenges when you are doing it is one thing to make one component and test it and do this, but when you are making a system, so you'll have to have a system approach. So that's why we call it a system engineers. So what we do is, but in your research, You are the system engineer, you are the component designer. So we are all, jack of all trades in a way. So we actually, when you start doing all these designs, we have to initially you have to spend a lot of time about looking about the integration part, that how everything will come together. And then we also do a lot of thermal analysis, because as you mentioned, one of the key thing is the mechanical and thermal. This is not, this is a multidisciplinary approach, because you can be the expert in electromagnetics, but if you have to really have input from mechanical engineers, thermal engineers, because you are generating heat and you don't want to heat up your sensors. That needs to be isolated somehow. So we actually do all those designs. We run simulations, like thermal simulation tools are available. We have to do mechanical structures in a way that it can survive vibration. So what we do, when we design an individual component, that we do all the tests on the component, not only the, let's say, electromagnetic test, like using a vector network analyzer or spectrum analyzer. Also, we do thermal vacuum test. So basically, put in vacuum, because at the end of the day, it will be in vacuum in space. So create vacuum, put it there, and then do a thermal recycling and see that how it behaves. So we have the detailed knowledge about thermal behavior in vacuum about these components. And then when we put it together, then we actually go through the same process for subsystems as well as the entire integrated system. So yes, integration is the key, that how everything will come together, and that the interfaces, if your one component is going to another component, let's say our front end, RF front end is connecting with the back end, digital back end. So that interface has to be really thought through beforehand, before you do the design part. So this has to, a lot of brainstorming, a lot of people have to work together on those. That's how we go about. And then at the end, when you put everything together, we'll have to do again, thermal test, vacuum test. I'll give an example like the MEMS structure, because MEMS are always, people say, oh, we'll have to be careful about MEMS and all. So we did a 10 million cycle, very high speed, basically into the voltage where the high voltage is connected. We connected through a kilohertz kind of source with that. So it very fast rate we did switching. So we did 10 million switching to see the lifetime test, that how does it perform under those many lifetime. We also do accelerated lifetime tests on the component. Let's say that you are using a spectrometer or a front end component, how it takes 7 years. If we are going to go to Europa, you are going to go to Jupiter, it takes 7 years. So how it's going to survive 7 years? So we can do accelerated lifetime testing. So we'll have to do all those things to make a space, space worthy hardware. So it takes, that's why it costs so much more money and time.
Okay, and Deepanjan has one more follow-up question. Are there multi-physics models required, and if so, are they available?
Yes, so we have, we use all kinds of different tools that is available. One of this for the electromagnetics, we use all this available, HFSS, and then CST, and we use ADS, from Agilent, that for circuit simulators, and then we use multi-physics tools for thermal analysis. ANSYS has a thermal analysis tool as well, and then all these thermal people also, they have other tools they prefer. So of course the mechanical design stress analysis for all this. So yes, actually it has, the tool situation has improved quite a lot. Many of the things that we are doing now, we could not have done a couple of years ago because the tools were not available, because it's very difficult. So a lot of things is coming together, and that's what is allowing us to make this kind of progress.
Sorry, I was muted. One second. Yeah, question by Kundan Kumar. What would be the required minimum gain of transmitting antennas for satellite communication?
Okay, it all depends on where you are going. So let's say you are going to Mars, right? So you'll have to really do a lot of calculations about your communication. You'll have to say the link budget you'll have to do. So on the ground, we have DSN, the Deep Space Network. On the ground, we have very big antennas. At Deep Space Network, we have at 3 places. That is, one is in Goldstone in California, the second one is in Madrid in Spain, and the third one is in Australia, because that is strategically placed so that we have 24/7 link available. So those are big antennas. However, your antennas on your spacecraft, we cannot put a very large antenna, right? So depending on what size of antenna that you can put, sometimes it is 50 centimeters is kind of big antenna. So we are doing at X band. Currently, most of our deep space communication happens in X band because that's where our infrastructure was. And then we sometimes get 50 dB gain, let's say, from an antenna that is on the spacecraft. And then we have huge gain for 70 centimeter dish antenna on the ground. So then you can go ahead and do your link budget and see what kind of power that we need. So it is about not only the gain of the antenna, it's about the total available power, your power budget, right? So we go and do that and then come up with what kind of antenna gain that we can put. But again, our hands are in a way tied because we cannot really put very large antenna, even if the requirement is that we need larger antenna, we cannot put. So we look at how can we increase the transmitted power. And nowadays we are looking at Ka band because, as you know, that if we go to Ka band, we can have a higher gain with similar antenna size, but the flip side to that is available power. So you have to think about that. Does it make sense to go to Ka band? Do we really gain? So we'll have to do all this link budget and see what actually comes out. So, but we are moving slowly towards a Ka band deep space network. But again, there are 2 different things when you're talking about your communication part, the data transmission of the satellites, and then other part is your actual instrument antenna, right? Because your instrument is getting data, the sensors that is connected with, but they are not transmitting the data back to Earth. So that is all different kinds of requirement based on what exactly you are doing, where you are going.
Okay. Another question is, how did you create a similar kind of environment like Mars to test and calibrate various systems of helicopter and also to test the antenna system? And a related question is, what is the estimated lifetime of the Mars helicopter?
Yes, so these are very good questions. In terms of creating that Mars environment, you'll have to do semi-vacuum, right? So as you said, the atmosphere of Mars is actually, I think 1/6 or 1/7. I'm not able to remember exact number, but like that. So we can create that. We can create a kind of semi-vacuum chamber. And it has to be big, like the way with the entire spacecraft we do thermal vacuum tests, right? Sometimes, so we have a huge vacuum chamber where we can do thermal vacuum tests, where it's kind of space environment. However, if you want to create Mars environment, it is not a fully vacuum, but some semi vacuum. So we create that, and then we do. We do those tests, and as for the lifetime, that I'll give an example. When the 2 rovers that we had sent, sometime back in 2001, 2002 time frame, their lifetime was 1 Mars year. 1 Mars year is much longer than 1 Earth year, about 4 years, let's say. However, they work for 15-20 years. So for a helicopter, it is about 1 Earth year is actual projected lifetime, because it is really about the battery power and everything. And also it is in a Mars environment. It has dust and everything. It all comes down to power on the solar panels. because dust covers the solar panels, and then the solar panels, they don't really work very well. The power goes down. So, however, we don't know. Let's see. Maybe it will work much longer the way that our twin rovers worked on Mars. So we'll see.
Okay. So another question is, it was mentioned that undergraduate students are working with CubeSats, but this would require a whole team and also the right mentorship. Any advice on how to start an undergraduate program on this in India?
Yes, you mentioned right mentorship. So you'll have to find your mentors. Talk to Varun, talk to Vinay, talk to Devdeep. Catch them, tell them to mentor you all, and Dipanjan and others, and Gaurav. So a lot of people are there at IISc. They can mentor you all. So yes, you'll have to form teams. But again, you think about not doing something really big. CubeSat frames are not very difficult to find. You can actually even make yourself a CubeSat frame, and then think about what kind of instrumentation that you want to put together. If it flies, what you are going to do. Build some sensors and stuff like that. So do not, try to go big, but attempt to solve a small problem and put something together hands-on. And then when you do testing and start doing some stuff, then approach ISRO or some private organization who can launch your satellite.
Okay. Okay. Another question is, what is the mesh used for the K-band 50 centimeter antenna to get acceptable surface accuracy?
Yes, so more than the mesh, it was these are kind of alloy, tungsten, gold, and a lot of kind of this alloyed mesh that we use, and of course we have to go through a lot of different experiments to make sure that it can survive the tension and everything. But it was more than the structure that is holding it, those ribs, so that when they deploy, they maintain the surface. So as you know that if we need about lambda by 40, lambda by 50 surface accuracy to have a good antenna. And then we actually did that with a lot of mechanical people are involved to make sure that when it deploys, those ribs maintained it's kind of the form, as well as you can see that at the edges, like an umbrella edges has this deep, it's not really like a normal reflector, a parabolic reflector at the edges. So we had to take that into account, make corrections for our design to make sure that those do not play much big role in terms of overall beam quality and all. So you are correct that we had to go through all these. Actually, first what we did, we actually made the antenna in total metal. However, that it was made it in a way that as if it is a kind of after deployment what we expected. So that kind of structure we made in metal first, and then did all our of course, we had done a lot of simulation, but we also did kind of a measurement on an entire metal structure. And then when we make the mesh antenna and then deploy, and then we compared and see what kind of performance we are getting. And it was very close, because nowadays the tools are so good that when you do a simulation and when you can do, if you can manufacture it well, you can keep those tolerances, then they are more or less, maps out well.
Okay. One more question. The meta surfaces you had shown, right? Would they be also actively tuned, or is that something?
No. You cannot do active tuning. If you think about active tuning at these frequencies, okay, it will be tough. You can do that. Maybe it's a good idea. Maybe you should think about actively tuning with some MEMS structures or some kind of piezoelectric structures. You can tune actively. So you can call it a, different kind of antennas. But yes, these are not really tuned. So they're all fixed in a way that you design it, all these structures, and then fabricate. You are not doing any active tuning. It's very difficult to do active tuning for this kind of structures.
Okay. Then last question is how is the correct mode excited in these meta surfaces, and how is the mode conversion also done?
Yes, so that is a good question. So basically, as I said, we need TM01 surface mode mode launcher. It was not easy to convert from, because our feed is a rectangular waveguide feed, but we did what we in our paper. If you go, you can see that what we did. We have a rectangular waveguide that's coming in. Then we actually do a Y junction kind of power splitter, and then there we transform that, and there is some impedance matching, because we calculate what is the metasurface impedance on the structure, and then we convert those two rectangular waveguides, with the impedance steps on them. Then we combine them in a circular waveguide structure from two sides, and from there you can actually create, you transform your T10 mode from the rectangular waveguide to TM01 mode in a circular waveguide. So in the paper, you'll be able to see, if you search for that, we showed the entire circuit, as well as how the feeds convert to a TM01 mode.
Okay. Okay. In the interest of time, we will conclude the webinar here. Thank you very much, Dr. Goutam, for this very interesting talk. So a lot of interesting ideas and very interesting effort in engineering, I think. Yeah, and then for the audience, stay tuned for the next webinar, which is going to be held on November 13th. It's given by Michael Bronstein from Imperial College London and Twitter UK. Okay, thank you very much and have a good evening.
Thank you. Thank you, everyone. Bye.